Hello, welcome to the TA training series on how to perform the CNC milling machine demonstration. As we move into this demo, it's important to keep in mind that the students have not yet had the lecture associated with this topic, so our expectations for their ability to answer questions that we ask related to it must be modest. Starting out, we ask them if they know what the acronym CNC stands for. Now usually, the students can come up with two of the three words, computer, controlled, and that's pretty good. Formally, we tell the students, computer numerical control refers to any machine tool, milling machine, lathe, bandsaw, etc., to which a computer system has been attached, which automates various motions and functions on the machine. Examples of this include axis motions, automatic tool changes, and the ability to automatically command any desired spindle speed. Moving through the demo, we want to emphasize 4 primary advantages and 4 disadvantages of the CNC technology, and it's important that you use the ones listed on the TA outlines because those are the ones I'm going to assess the students on at the end of the semester. Starting with the advantages, the first one is the ability of a CNC machine to command multiple axes of simultaneous motion. The easiest way to explain this to the students is to take a workpiece and pick up an example cutting tool. Of course, be careful of the cutting end and try not to touch the precision machine taper as well. So pick up the tool and tell the students, when they learned how to use the milling machines, for example, we taught them they could move the x-axis or the y-axis. However, if they tried to move both the x and y-axis, they couldn't do so very accurately because they're essentially using the machine like an old school Etch-a-Sketch. A CNC machine, however, can accurately control multiple axes of simultaneous motion. So show the students an example of a CNC part, and then with the tool in your hand, explain that a CNC could move both the X and the Y axes of motion simultaneously in an accurate fashion in order to move this tool in the circular pattern required to produce this pocket, the circular pocket or circular bore. The second advantage that we want to highlight is the suitability of CNC machines for mass production. Since CNCs use a computer and software to control them, once we get the machine to perform a desired feature or create a desired part, then it's very easy for the machine to do the same thing over and over and over. It removes the human element that is plagued by things like fatigue and just mistakes that we will commonly make, and it's always going to give us a part that is a replica of the last part it made. A third advantage of CNC machines, which the students will see today during the demonstration, is their ability to automatically change tools once they're loaded into the tool carousel or tool turret. The fourth and final advantage that we're going to talk about with the students is the ability that most CNC machines have to use either high pressure air and oil mist, as we have on this machine, or high pressure liquid coolant, like we have on the VF2 CNC milling machine, to flush chips out of the cutting zone, ensuring that they don't get recut, improving part accuracy, improving part surface finish, and keeping the tools and the workpieces much cooler. Those are the 4 advantages we want to highlight, and then there are 4 disadvantages that we wish to discuss with the students as well. The first disadvantage is usually one that the students are able to come up with on their own, and that's the price or the cost. This TM2 CNC milling machine costs about $60,000. The Bridgeport 3-axis manual milling machines that we taught the students how to use, or we trained them on the basic safety of, those machines cost about $15,000. So the basic CNC milling machine behind me costs 4 times as much. A second disadvantage is the fact that to use a CNC machine, I need some extra skill sets. I need the ability to write a program and also need to be able to debug that program. I like to ask the students how many of them have taken a programming class with a show of hands. And usually they can tell me, or they will agree, that one of the first things you learn when trying to program is that it always requires debugging to get the program to do what you really intended for it to do. And it's no different on a CNC machine. Okay, so the second disadvantage is that we have to have a programming and debugging skill set in order to use the machine. A third disadvantage that we want to emphasize is that CNC machines can actually, and surprisingly to most, be slower and more expensive to make one simple part. The time that it takes to load the tools and teach the CNC machine how long they are and what size they are, as well as write the program, debug the program, and then carefully run the program the first time when they're making that part, is often that it requires more time than simply taking the simple part, moving over to a manual machine, and either producing the part or the required features. Okay? So a CNC machine can actually be slower and more expensive to make low quantity, simple parts on. And the last disadvantage that we want to emphasize with the students during this demo is the fact that CNC machines always require more facility resources. As we can see here, this 3-axis mill, although it's comparable in work area to one of our Bridgeport milling machines, it requires much more floor space because it has a large electrical cabinet on the back side. It also has a large pendant on the front side for the operator, takes up some extra space over here for the tool carousel, etc. So they usually, or CNCs always, take up more floor space than comparable sized manual machines. In addition, they require more power. And finally, they're always going to necessitate more frequent maintenance because of all the additional electronics that they have. They have computers, they have hard drives. We know the hard drives are going to crash eventually. We know that electronics can wear out, limit switches, position encoders, things like that nature. They are going to wear out over time and require more frequent maintenance than a manual machine, which doesn't possess most of those electronic features. Having emphasized or having discussed the 4 pros and the 4 cons that I just outlined, now it's time to move into the actual demonstration itself. I'm going to move the camera's focus over to the machine console, and as I talk through it, my hope is that the camera will allow you to see the keystrokes to begin to familiarize yourself with where the various functions and buttons on the machine reside, and then come in and run through the demonstration with the assistance of a senior TA so that you begin to develop an understanding of not just running the machine, but a confidence of where to find the different functions on the machine. Let's do that now. Next, we turn the machine on. As noted on the TA outline, students don't have to see this part. You can do it a few minutes before each lab begins or while the students are cleaning up their lathe. The first step is to press the green power on button located at the top left-hand corner of the machine console. As noted on the TA outline, it typically takes about 60 seconds for the CNC's computer to boot. Once booted, we are greeted by the machine's initialization screen or introduction screen, at the bottom of which we are directed to press any key to continue. Moving on to step number 2, press the orange reset button twice. The first time we press the reset button, clears the initialization screen. The second time we press the button, clears the alarm message, which tells us the machine's servo motors are currently off. As noted on the TA outline, step number 3 is optional, and it should not be used by TAs who have given the demonstration for less than 3 semesters. Step number 3 tells us how to override the safety switch on the CNC Machining Center, but this is only a function that experienced TAs who strongly understand the necessary safety to run the machine with this switch disabled can use. Step number 4 tells us to press the blue power-up restart button to initialize the machine servos. This button is located to the right of the orange reset button. If we press it, we notice an alarm message is generated which says safety switch. In this case, we have to retrieve the dead man safety switch off the back side of the machine, press the button and hold it, and then press the power up restart button on the CNC. At this point, as noted on the outlines, the machine will start moving, so you need to direct everyone to stand back. The axes will home, and the tool changer will change automatically to tool number 1.
Next, we load the part. As instructed in step 5, press the Y button on the alphanumeric keyboard and then press the home button. This will bring the Y axis towards the operator for easy part loading. When loading the part into the rotary vise, align the top of the part with the top of the chuck jaws using your fingers, a parallel, or a 6-inch ruler. Most importantly, be careful to never clamp on the shoulder diameter, as this will cause the probe to encounter the part a half an inch above the location where it expects to find it. Next, we load the program. As stated in step 7, press the List Programs button and select the Memory tab to display the programs listed in the CNC's memory. Use the hand wheel to scroll through the programs until you find the desired one. In this case, it's program number 10007. You will find the program name listed to the right of the program number. Once you have the correct program highlighted, press the Select Program button on the operator console. You will notice there is a capital A next to the program number at this point, denoting it is the active program. Now, let's examine a few of the common G&M codes used to program the CNC machine so we can show the students an example of the programming language. The first part of the program contains the program number, followed by a few comments describing the program. The next line is typically referred to as the safety block. It includes common codes that are used to initialize the machine before each regular use. G0, for example, places the machine in rapid positioning mode. G17 tells the machine that all circular motion is to default occur in the XY plane. G20 is inch mode as opposed to metric. G80 cancels any previously running canned cycles like a drilling cycle or a tapping cycle. And finally, G90 places the machine coordinate system in absolute mode as opposed to incremental. The next part of the program performs the Z-surface part probing. The T20 M06 line commands the CNC machine to change to tool number 20. The M06 is an example of an M code, or miscellaneous code. In this case, that forces the CNC machine to initiate the tool change sequence. The T20 without the M06 following it would result in no motion on the CNC machine. The next line contains a G43 H20. G43 is an example of a G code, which means geometry code. In this case, G43 H20 tells the CNC machine to initiate the tool length offset for tool number 20. The G57 tells the machine which local work coordinate system is being used. The G0 again tells the machine to rapidly move into position, and the X0 Y-0.75 tell the CNC machine to move the tool probe stylus to those coordinate locations. Up to this point, there has been no Z motion of the tool probe. That occurs on the following line with the Z5 command. In this case, the Z5 instructs the CNC machine to rapidly move the tip of the probe's ruby to a distance equal to 5 inches above the previously probed workpiece position. The M00 command on the following line is known as a program stop. This function forces all motion on the machine to cease until the operator presses the cycle start button. Each M00 is followed by a comment in parentheses. This comment is an instruction to the operator, so you should make sure that you always read it each time you encounter an M00 in the CNC demo. In this case, the comment is instructing the operator to make sure the rapid feed rate is turned down to 5 or 25% of its maximum rate to ensure that the probe tip does not approach the workpiece in too rapid of a manner. The next line causes the tip of the ruby probe to rapid down to 0.3 inches off the top surface of the workpiece at the rapid feed rate previously selected. The M00 is at this location, so the program execution pauses while you explain the probing sequence to the students. The next line of importance is the G65, which is a program subroutine call. The P, A, and S blocks are parameters passed to the subroutine, so it knows what probing cycle to run and which work offset to store the subsequent probing value in. After the probing sequence is complete, the program instructs the probe to move 5 inches above the workpiece and pause while you finish explaining the probing sequence to the students. The next part of the program performs a tool change to load tool number 3, which is the .157 tap drill for the 1024 threads. The next block instructs the CNC to rapidly move the tap drill to X0, Y minus 0.75, and position the tip of the tap drill exactly 5 inches above the top surface of the workpiece. At this point, an M00 pauses program execution so that you can check that either oil has been placed on top of the workpiece in the location where the holes will be drilled, or that you have turned on the air oil misting system present on the CNC. The next block contains a spindle speed command of 4,000 RPM, followed by an MO3, which commands the CNC to turn the spindle on in the clockwise direction. The next line commands the CNC to rapidly move the tip of the tap drill to 0.1 inches above the top surface of the workpiece. The final portion of the program we will review in this video is the part that actually performs the PEC drilling cycle. G83 is the PEC drilling function call, and it is followed by several parameters. The Z parameter instructs the CNC to drill each hole 0.7 inches deep. The R parameter tells the CNC to retract the drill bit 0.1 inches above the part surface upon each PEC. The I parameter is the amount for the first PEC. The J parameter instructs the CNC to reduce each subsequent PEC by 50,000ths of an inch. The K parameter is the minimum allowed depth of PEC, and the F parameter is the feed rate used for the drilling cycle. When the G83 program line is executed, the CNC machine will tap drill the first hole at the current spindle location. The machine will then execute the identical motion at the following 6 Cartesian coordinate clusters. After the G83 canned drill cycle is complete, the G80 cancels the cycle, the M09 turns the machine's coolant system off, and the M05 turns the spindle off. Although we've spent about 6 minutes reviewing the program in this TA training video, as noted on the TA outline, you should spend about 2 minutes only hitting a few of these highlights with the students. The goal is not to turn the students into CNC programmers during this demo, but rather to allow them to understand that with a little bit of practice, anyone could program the machine because it uses a logical programming language. When you are finished explaining the program to the students, it's crucial to remember to press the reset button, which rewinds the program pointer to the beginning of the program. Failure to follow this important step will prove catastrophic. The final step when loading the program is to press the memory mode button. Now we are ready to run the program and make the part. As instructed in steps 11 and 12, set the spindle speed and feed rate override, as well as the rapid override, all to 100%. We can do this because our program has been run many times, so we are confident of its accuracy. Start the program by pressing the green cycle start button with your left thumb while hovering your right thumb over the red feed hold button in case you quickly need to stop the machine. After pressing the cycle start button, the machine immediately performs a tool change and rapids the tool probe to 5 inches above the workpiece. The program comment accompanying the M00 program stop at this location instructs the operator to turn the rapid override down to 5% to 25%, whatever he or she is comfortable with at this point running the machine. Pressing cycle start causes the probe to rapid down to within 0.3 inches of the part surface, again pausing when waiting for you to explain the probing cycle to the student before pressing the cycle start button again to initiate the actual probe cycle. Once the probe measures the top surface of the workpiece, it rapidly retracts and stops at a distance of 5 inches away from the part to allow you to answer any questions the students had about the probing cycle before pressing the cycle start button to continue with the tool change. As directed in the program, after loading the tap drill, the CNC rapids it to within 5 inches of the part surface. This is a convenient time to explain the tap chart and ensure the students understand why we are using a .157 drill bit, as well as explain the difference between the standard and split point drill bits. Before continuing, add a generous amount of oil to the top surface of the part and the drill bit itself. Press cycle start to continue program operation. Mention that we still have to peck drill for chip evacuation even though we're using a CNC machine. As you can see in the video, I prefer to apply the oil to the part manually versus using the air oil mister on the machine because the mister is more difficult to talk over. However, when applying the oil manually, after the machine drills or taps 3 or 4 holes, reapply a little bit of oil to the drill or tap. When the tap drilling is complete, the CNC rapids the tap drill away from the part in preparation for a tool change and pauses while you answer any questions the students may have about this part of the program. Pressing the cycle start button initiates the tool change sequence, after which the CNC immediately rapids the tap to within 5 inches of the part surface. Before continuing, add a generous amount of oil to the top surface of the part and the tap itself. Before pressing cycle start to continue program operation, explain the rigid tapping sequence to the students so they understand what they are about to watch. Rigid tapping synchronizes the rotational velocity of the tap with the linear feed rate of the z-axis in order to create a perfect thread in the workpiece. Just like manual tapping, it also uses a peck tapping technique to clear the chips so the tap does not break. After the machine taps 3 or 4 holes, reapply a little bit of oil to the tap. Once the rigid tapping cycle is complete, the CNC will rapid the tap away from the part in preparation for the next tool change. Pressing cycle start for the final time removes the tap from the spindle and moves the y-axis towards the operator for easy part removal. After blowing the chips off the part and wiping the oil off of it, you should use a 1024 screw to check the threads and the screw also makes a convenient handle to hold on to when removing the part from the vise. If unloading the part by yourself, be careful not to drop it accidentally into the center of the vise. I hope you enjoyed watching this video as much as I enjoyed making it for you. And thank you for watching another Turtle Time production.